This is lab 5. So the purpose of this lab is to observe Faraday's law with a bar magnet falling through a conductive tube of aluminum foil. Uh, and it is to model the magnet going through the tube in glow script. It is also to compare the observed data to the computational model. The results of this lab are that the average falling time for the magnet is 0.3546 seconds. The predicted falling time for the glow script model with a magnetic dipole of 1.446 amps times meter squared, which is from lab 3, is 0.326 seconds, and the predicted time is consistent with the observed time. Sorry. The error could have occurred while measuring the dimensions of the aluminum tube. They could have also occurred when recording for the time of the magnet to fall. There could have also been other magnetic fields interfering with the falling time of the magnet. Fundamentals of this lab are Faraday's law, magnetic flux, which relates the external magnetic field and the area. The change in magnetic flux of a dipole is given right there. The derived magnetic force equation is I times 2 pi r b sine theta. Ohm's law is I equals V over R. And then Newton's third law tells us that the magnitude of the magnetic force on the loop due to the dipole is equal to the magnitude of the magnetic force by the loop on the magnet. So the model is the bar magnet as a magnetic dipole and the aluminum foil tube as the conducting tube. And the assumptions are that only the force of gravity and the magnetic force are acting on the magnet. So the system is the aluminum tube and the bar magnet, and the surroundings is everything else. The procedure is that I marked the north pole of the magnet using the magnetometer app. And then I measured the radius, the thickness of the aluminum foil, and the length of the tube. Then measured the mass of the magnet, and then dropped the magnet through the tube 5 times and record the time it takes for the magnet to reach the bottom, and then computationally model this in GlowScript. The observations were that the magnet took much longer than expected to fall through the conductive tube due to the magnetic force it experiences canceling out the force of gravity. This causes it to fall at a constant speed. And these are the measurements I found. So these are the 5 trials, and then the average at the bottom, and then all of the other measurements of the magnet itself and the aluminum foil tube are on the right. The magnetic dipole, which is from lab 3, is 1.446 amps times meter squared, which is not very strong. So the magnetic force didn't cancel the force of gravity as much as it should have. This is the glow script model. So as you can see, these are all like the constants, and these are the functions that are created to create this model. Which shows the velocity versus time, and on the top is the tube, and that ring is one of the rings that shows the induced current in the aluminum foil. And the average time of 0.326 seconds from the computational model is consistent with the average time of 0.546 seconds found in the experimental data. So interpreting the simulation, which color in the simulation represents clockwise and counterclockwise? So blue represents clockwise current and the red represents the counterclockwise current. This is because as the magnet is dropping, the lower ring is red, which is the current that is induced by the north pole of the magnet and therefore is counterclockwise current because the B field should point up. And the blue is the current induced by the south pole of the magnet, which is the clockwise current. What happens to the dynamics of the system if the magnet is flipped? The dynamics would be the same as the induced currents would still create the forces to push the magnet up. So there'd be no change in the dynamics of the system. How is the total time for the real world system compared to the computational model? So the computational model is consistent with the real world system. The computational system can be made more accurate by accounting for any friction between the sides of the tube and the magnet and any other errors that were found in the real world system. And what does the shape of the velocity versus time graph reveal at the forces acting on the magnet? It reveals that the forces should cancel out to be zero, but obviously, since this magnet isn't as strong, uh, the force wasn't completely canceled. Discussion. So what if the resistivity of the conductor were reduced to as close as possible to zero, and how would the dynamics change? Nearly zero resistivity would mean that nearly zero resistance. This would mean that there would be an extremely large current and therefore extremely large magnetic force. This would cause the magnet to fall much lower in the tube. And if there are holes or slots cut into the tube, this would reduce the induced current, causing the magnetic force to decrease. And the gravitational force would then be much stronger than the magnetic force. This would make the magnet fall faster. Finally, for the conclusion, Faraday's law is an important part of our everyday lives, and it can be modeled with bar magnets and conductive tubes. Thank you.